Hello, my name is Aaron Thomas, and today I'm going to be talking about the math behind HIV and other viruses. For a brief overview, I'm going to be talking about how viruses like HIV spread throughout the body. I'll be talking about the differential equation for virus spread. I'll solve the differential equation for virus spread, and I'll find the initial values for it too. And at the end, I'll do a brief conclusion. So to begin, we have our happy-go-lucky T cell. T cells are part of a group of white blood cells known as lymphocytes. They mature in the thymus, which is where the T in T cell comes from, and they defend the body from infectious disease, as all white blood cells do. And then we have our villainous HIV virus. These small infectious agents replicate inside the living cells of other organisms, whether they be plants, animals, or, in the case of the HIV virus, inside us. They attack the T cells of the immune system. Fun fact, a single virus particle is called a virion. So now I'll begin explaining the process of infection. So the way this all begins is that a virion of HIV comes in contact with a healthy T cell. What ends up happening is that when they make contact, the virion connects to the outside of the healthy cell and starts to merge with it. Once the virion merges with our T cell, it will hijack the inner workings of the cell and force it to make more and more HIV virions. Once the T cell produces a ton of virions, it will then burst and release virions into the bloodstream. The process will repeat over and over again. This is where the danger of HIV steps in. As the T cells are being hijacked, they cannot properly defend the body from harm of other things like influenza, or even the common cold when you get down to it. This is where the math sets in. Here we have our three differential equations. The first finds the rate of change in the population of healthy T cells. The second finds the rate of change in the population of infected T cells. And the third finds the rate of change in the population of the virions. Where T of T is equal to the population of uninfected T cells at time t. I of T is the population of infected T cells at time t. B of T is the population of virions at time t. Then we have the constant input source of healthy T cells per day, the normal loss rate of constant uninfected T cells per day. We have the infection rate constant, the loss rate constant. We have the loss rate of virions, and we have the number of virions produced per day per T cell. Now we're going to be talking about treatment. Let's assume that the treatment for this patient is 100% effective. If so, beta, which in the last slide we discussed was the infection rate constant, is 0. Knowing this, you can remove half of the first two differential equations, then solve them. In particular, I used the separation method. The results can be seen at right. I like to point out that in the equation for the change of Vt, I of t was used. Now that we know what I of t is from the last slide, I was able to solve for V of t, as you can see here. Now that we have these, we can find the initial values for the differential equation. Now that time is 0, we could find the constants generated by integrating to solve the dE. Given data taken from patient, we could find the minimum amount of time that it could take to cure HIV, or any virus for that matter. In conclusion, HIV is a potentially deadly disease that attacks the immune system. The spread of HIV can be calculated using a model, which we discussed earlier on. By assuming that the treatment is 100% effective, one can calculate the minimum amount of time that it could take to rid the body of HIV. This model can be used for other viruses as well.